Chapter 8. The Scientific Experiments. After a year of concentrated effort in which the resources of NASA, the Jet Propulsion Laboratory, and American science and industry had been marshalled, Mariner 2 had probed secrets of the solar system some billions of years old. Scientists and engineers had studied the miles of data processed in California from the tapes recorded at the 5 DSIF tracking stations around the world. 2.5 months of careful analysis and evaluation yielded a revised estimate of Venus and of the phenomena of space. As a result, the dynamics of the solar system were revealed in better perspective, and the shrouded planet stood partially unmasked. When the Mariner data were correlated with the data gathered by JPL radar experiments at Goldstone in 1961-62, the relationships between the Earth, Venus, and the Sun became far clearer than ever before. 2 experiments were carried on the spacecraft for a close-up investigation of Venus's atmosphere and the temperature characteristics: a microwave radiometer and an infrared radiometer. They were designed to operate during the approximate 35-minute encounter period, and at a distance varying from about 10,200 miles to 49,200 miles from the center of the planet. Table of equipment. The microwave radiometer determines the temperature of the planet's surface and details concerning its atmosphere. The experimenters were Dr. A. H. Barnett, Massachusetts Institute of Technology; D. E. Jones, JPL; Dr. J. Copeland, Army Ordnance Missile Command and Ewan Knight Corps; Dr. A. E. Lilly of Harvard College Observatory. The infrared radiometer was to determine the structure of the cloud layer and temperature distributions at cloud attitudes. The experimenters were Dr. L. D. Kaplan, JPL and University of Nevada; Dr. G. Neubauer, JPL; Dr. C. Sagan, University of California, Berkeley, and Harvard College Observatory. The magnometer was there to measure planetary and interplanetary magnetic fields. The experimenters were P. J. Coleman, NASA; Dr. L. Davis, Caltech; Dr. E. J. Smith, JPL; Dr. C. P. Sonnet, NASA. The ion chamber and matched Geiger-Müller tubes was there to measure high-energy cosmic radiation. The experimenters were Dr. H. R. Anderson, JPL; Dr. H. V. Neyer, Caltech. The Anton Special Purpose Tube was there to measure lower radiation, especially near Venus. The experimenters were Dr. J. Van Allen and L. Frank of State University of Iowa. The Cosmic Dust Collector was there to measure the flux of the cosmic dust. The experimenters were W. M. Alexander of Goddard Space Flight Center, NASA. The Solar Plasma Spectrometer was there to measure the intensity of low-energy positively charged particles from the Sun. The experimenters were M. Neubauer and Dr. C. W. Snyder, JPL. 4 experiments for investigation of interplanetary space and the regions near Venus were employed: a magnometer, high-energy charged particle detectors, including an ionization chamber and Geiger-Müller radiation counters, a cosmic dust collector, and a solar plasma detector. These 6 scientific experiments represented the cooperation efforts of scientists at 9 institutions: the Army Ordnance Missile Command, the Ewan Knight Corps, the California Institute of Technology, the Goddard Space Flight Center of NASA, Harvard College Observatory, the Jet Propulsion Laboratory, the Massachusetts Institute of Technology, the state universities of Iowa and Nevada, and the University of California at Berkeley. The table above listed the experiments, the experimenters, and their affiliations. At the Jet Propulsion Laboratory, the integration of the scientific experiments and the generation of a number of them were carried out under the direction of Dr. Manfred Eimer. R. C. Wyckoff was the project scientist, and J. S. Martin was responsible for the engineering of the scientific experiments. Data Conditioning System. Mariner's scientific experiments were controlled and their outputs processed by a data conditioning system, which gathered the information from the instruments and prepared it for transmission to Earth by telemetry. In this function, the data system acted as a buffer between the science systems and the spacecraft data encoder. The pulse output of certain of the science instruments was counted, and the voltage amplitude representations of other instruments were converted from analog form to a binary digital equivalent of information signal. The data conditioning system also included circuits to permit time sharing of the telemetry channels with the spacecraft engineering data, generation of periodic calibration signals for the radiometer and magnometer, and control of the direction and speed of the radiometer scanning cycle. During Mariner's cruise mode, the data conditioning system was used for processing both engineering and science data. If the spacecraft lost lock on the Sun or the Earth during the cruise mode, no scientific data would be telemetered during the reorientation period. Engineering data were sampled and transmitted for about 17 seconds during every 37-second interval. The planetary encounter mode involved only science and no engineering data transmission. In this mode, the science data were sampled during 20-second intervals. Cosmic Dust Collector. The Cosmic Dust Collector on Mariner 2 was designed to measure the flux, density, direction, and momentum of interplanetary dust particles between the Earth and Venus. These measurements were concerned with the particles' direction and distance from the Sun, the momentum with respect to the spacecraft, the nature of any concentrations of the dust in streams, variations in cosmic dust flux with distance from Earth and Venus, and the possible effects on manned flight. Mariner's cosmic dust instrument could detect a particle as small as something like a billionth of a gram, or about 5 trillionths of a pound. This type of sensor had been used on rockets even before Explorer 1. It had yielded good results on Pioneer 1 in the region between the Earth and the Moon. The instrument was a 55 square-inch acoustical detector plate, or sounding board, made of magnesium. A crystal microphone was attached to the center of the plate. The instrument could detect both low and high momentum particles, and also provide a rough idea of their direction of travel. The dust particle counters were read once each 37 cycles during the cruise mode. This rate was increased to once every 20 seconds during the encounter with Venus. The instrument was attached to the top of the basic hexagonal structure. It weighed 1.85 pounds and consumed only 0.8 watts of power. Solar Plasma Experiment. In order to investigate the phenomena associated with the movement of plasma, charged particles of low energy and density streaming out from the Sun to form the so-called solar wind in interplanetary space, Mariner carried a solar plasma spectrometer that measured the flux and energy spectrum of positively charged plasma components with energies in the range of 240 to 8,400 volts. The extremely sensitive plasma detector unit was open to space, consumed 1 watt of power, and consisted of 4 basic elements: curved electrostatic deflection plates and collector cup, electrometer, a sweep amplifier, and a programmer. The curved deflector plates formed a tunnel that projected from the chassis on the spacecraft hexagon in which the instrument was housed. Pointed towards the Sun, the gold-plated magnesium deflector plates gathered particles from space. Since the walls of the tunnel each carried different electrical charges, only particles with just the correct energy and speed could pass through and be detected by the collector cup without striking the charged walls. A sensitive electrometer circuit then measured the current generated by the flow of the charged particles reaching the cup. The deflection plates were supplied by amplifier-generated voltages, which varied in 10 steps, each lasting about 18 seconds, allowing the instrument to measure protons with energies in the 240 to 8,400 electron-volt range. The programmer switched in the proper voltage and the resistances. High-energy radiation experiment. Mariner carried an experiment to measure high-energy radiation in space and near Venus. The charged particles measured by Mariner were primarily cosmic rays, protons or the nuclei of hydrogen atoms, alpha particles, nuclei of helium atoms, the nuclei of other heavier atoms, and electrons. The study of these particles in space, and those which might be trapped near Venus, was undertaken in the hopes of a better understanding of the dynamics of the solar system and the potential hazards to manned flight. The high-energy radiation experiment consisted of an ionization chamber and detectors measuring both particle flux, velocity times density, all mounted in a box measuring 6 by 6 by 2 inches and weighing just under 3 pounds. The box was attached halfway up the spacecraft superstructure in order to isolate the instruments as much as possible from the secondary emission particles produced when the spacecraft was struck by cosmic rays, and to prevent the spacecraft from blocking high-energy radiation from space. The ionization chamber had a stainless steel shell 5 inches in diameter, with walls only 1/100th of an inch thick. The chamber was filled with argon gas, into which was projected a quartz fiber next to a quartz rod. A charged particle entering the chamber would leave a wake of ions in the argon gas. Negative ions accumulated on the rod, reducing the potential between the rod and the spherical shell, eventually causing the quartz fiber to touch the rod. This action discharged the rod, producing an electrical pulse which was amplified and transmitted to the Earth. The rod was then recharged and the fiber returned to its original position. In order to penetrate the walls of the chamber, protons required an energy of 10 million electron volts, MeVs. Electrons needed 0.5 MeV and alpha particles 40 MeV. The particle flux detector incorporated 3 Geiger-Müller tubes, 2 of which formed a companion experiment to the ionization chamber. Each generated a current pulse whenever a charged particle was detected. One tube was shielded by an 8/1000th of an inch thick stainless steel sleeve, the other by a 24/1000th inch thick electron-stopping beryllium shield. Thus the proportion of particles could be determined. The third Geiger-Müller tube was an end-window Anton-type sensor, with a mica window that admitted protons with energies greater than 0.5 MeV and electrons, 40,000 electron volts. A magnesium shield around the rest of the tube enabled the instrument to determine the direction of particles penetrating only through the window. The 3 Geiger-Müller tubes protruded from the box on the superstructure of the spacecraft. The end window tube was inclined 20 degrees from the others, and 70 degrees from the spacecraft's sun line, since it had to be shielded from direct solar exposure. The magnometer. Mariner carried a magnometer to measure the magnetic field in interplanetary space and in the vicinity of Venus. Lower sensitivity limits on the instrument was about 5 gamma. A gamma is a unit of magnetic measurement and is equal to 10 to the power of 5, or 1/100,000th Oersted, or 1/30,000th of Earth's magnetic field at the equator. The nails in your shoes would probably produce a field of about 1 gamma at a distance of approximately 4 feet. Housed in a 6 by 3 inch metal cylinder, the instrument consisted of 3 magnetic core sensors, each aligned on a different axis to read the 3 magnetic field components, and having primary and secondary windings. The presence of a magnetic field altered the current in the secondary winding in proportion to the strength of the field encountered. The magnometer was attached near the top of the superstructure, just below the Omni antenna, in order to remove it as far as possible from any spacecraft components having magnetic fields of their own. An auxiliary coil was wound around each of the instrument's magnetic sensor cores to compensate for permanent magnetic fields existing in the spacecraft itself. These spacecraft fields were measured at the magnometer before launch, and in flight, the auxiliary coils carried currents of sufficient strength to cancel out the spacecraft's magnetic fields. The magnometer reported almost continuously on its journey and for 20 days after the encounter. During the encounter, observations were made each 20 seconds on each of the 3 components of the magnetic field. Microwave radiometer. A microwave radiometer on board Mariner 2 was designed to scan Venus during encounter at 2 wavelengths, 13.5 and 19 millimeters. The radiometer was intended to help settle some of the controversies around the origin of the apparently high surface temperature emanating from Venus and the value of the surface temperature. The equipment included a 19-inch diameter parabolic antenna mounted above the basic hexagonal structure on a swivel driven in a 120-degree scanning motion by a motor. The radiometer electronic circuits were housed behind the antenna dish. The antenna was equipped with a diplexer, which allowed it to receive both wavelengths at once without interference, and to compose the signals emanating from the two reference horns with those from the planet. The reference horns were pointed away from the main antenna beam, so they would look into deep space as Mariner passed Venus. This feature allowed the antenna to bring in a reference temperature of approximately absolute zero during the encounter. The microwave radiometer was to be turned on 10 hours before the encounter began. An electronic motor was then to start a scanning or nodding motion of 120 degrees at a rate of 1 degree per second. Upon the radiometer contact with the planet, this scanning rate would be reduced to 1/10 of a degree per second as long as the planetary disk was scanned. A special command system in the data conditioning system would reverse or normalize the direction of scan as the radiometer reached the edge or limb of the planet. The signals from the antenna and the reference horns were to be processed and the data handled in a receiver located behind the antenna, which measured the difference between the signals from Venus and the reference signals from space. The information was then to be telemetered to the Earth. The microwave radiometer was automatically calibrated 23 times during the mission by a sequence originating in the data conditioning system, so that the correct functioning of the instrument could be determined before the encounter with Venus. Infrared radiometer. The infrared radiometer was a companion experiment to the microwave instrument, and was rigidly mounted to the microwave antenna so that both radiometers would look at the same area of Venus with the same scanning rate. The instrument detected radiation in the 8 to 9 and 10 to 10.8 micron regions of the infrared spectrum. The infrared radiometer had two optical sensors. As the energy entered the system, it was chopped by a rotating disk, alternately passing or comparing emissions from Venus and that of empty space. The beam was then split by a filter into two wavelength regions. The output was then detected, processed, and transmitted to the Earth. The infrared radiometer measured 6 inches by 2 inches, weighed 2.7 pounds, and consumed 2 watts of power. The instrument was equipped with a calibration plate, which was mounted on a superstructure truss adjacent to the radiometer. Mariner's scientific objectives. Equipped with these instruments, and with the mechanism for getting the measurements back to Earth, Mariner 2 was prepared to look for the answers to some of the questions inherent in its overall mission objectives. 1. The investigation of interplanetary space between Earth and Venus, measuring such phenomena as the cosmic dust, the mysterious plasma or solar winds, high-energy cosmic rays from space outside of our solar system, charged particles from the Sun, and the magnetic fields of space. 2. The experiments to be performed near Venus, at about 21,150 miles out from the surface, in an effort to understand its magnetic fields, radiation belts, the temperature and composition of its clouds, and the temperature and conditions on the surface of the planet.